Good evening, everyone. I hope I'm audible. Welcome to the week 11 live interaction session for the course on renewable energy engineering, solar, wind, and biomass energy systems. Yes, okay. Yeah, so welcome to the course. Welcome to the live interaction session for the course on renewable energy engineering, solar, wind, and biomass energy system. Let's just wait for a few minutes for others to join before we begin our session for today. So I think we can start our session for today. Let me just present my screen. I hope my screen is visible as well as I'm audible. Yeah, okay, yeah. Thank you so much. So I welcome you all for the week line interaction session for the course on renewable energy engineering, solar, wind and biomass energy systems. Myself Pratyumnan, a PhD scholar at the Indian Institute of Technology, the NPTEL course member for conducting the live interaction session every week. This course is offered by Professor Vaibhav Vishant Gaut sir and Professor Anandalakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati under the NPTEL program. So, for the last four sessions, we primarily focused our interest towards understanding how biomass is an energy source. Particularly speaking, how biomass can be used as a renewable energy resource. How biomass is actually a cheap and a renewable energy resource which can be harnessed, and we saw the interdependency of the solar energy and the biomass energy systems. We saw the different types of biomass feedstocks or biomass raw materials that are available from the nature. We then went through the physical characterization of the biomass, if you remember, like the fixed the amount of moisture content, the inorganic content that is present in the material, and we also saw the ultimate analysis, that is where we wanted to find out the percentage of carbon, percentage of nitrogen, percentage of sulfur that is present in our biomass sample. So the characterization entire part we dealt in detail. One is the proximate analysis, which is nothing but more often the physical characterization of your biomass, such as density, moisture, percentage of ash, and another one is your ultimate analysis, where we focused on finding the percentage of each element that is present in your biomass. After that, we uh, we focused on converting your biomass towards energy source. There were two different type of processes. There are two different type of major process. One was your thermal treatment and another one was your thermochemical treatment. So in your thermal treatment, you just burn your biomass and obtain the energy that comes from the burning your biomass. And in case of the chemical treatment, you actually subject your biomass to different kind of chemical treatment and then obtain the fuels out of that, such as your bioethanol, biobutanol, and other different kinds of fuel from your biomass, and use that fuel for different applications. So in that, you actually saw the ethanol fermentation and the biogas production. And in case of the thermal treatment, we focused on three different processes majorly. One was your pyrolysis, and another one was your gasification and the combustion, and the difference between each of this process, like what is the, how does subjecting your biomass to different conditions actually give us different products, and what is these different conditions, how they vary with each other. We saw the liquefaction process of the hydrocarbons, the torrefaction process, and then we also solved almost a lot of problems on each of the concepts as we went through the 4 week of live interaction session, as well as the course on biomass energy systems. So this week onwards, we will see how wind energy is a renewable energy resource. But before moving on to that, we actually saw last week a question. Let me just open that question. Yes, this question number 3 on biomass, where it was based on the concept of combustion, and we solved the A part of that question, but I asked the audience as well as you guys to actually solve it for yourself and come back with the answer during this week's live interaction session. So if you have solved this B part of the question, then you can actually let me know the answer. What was your answer for this calculating the equivalence ratio if you burn your propane in an air fuel mixture of ratio 18:1? Have you tried solving this question? Okay, okay, yeah, that's not an issue. Can you just try solving it now and letting me know the answer, and let me know the answer? It's very simple. Uh, it is very similar to what has been solved for the part A, but it's just that you need to calculate the air to fuel stoichiometric ratio. Once you do that, you will be able to calculate the equivalence ratio. So the equation, let me just write the equation so that it will be easy. So you know propane is C3H8. and that you are going to react with the air. And here, since we are asked to find out the air to fuel in stoichiometric ratios, so you will not be having the concept of excess of air, unlike in the previous examples that we saw, like 40% excess air or 30% excess air. Here we will be taking exactly the stoichiometric quantity of air that we require for our combustion process. So that will be so since nitrogen is an incombustible and inert gas, so that will not be reacting with any of your hydrocarbons or other kind of components that you will be feeding into your burner or your system. So that part of the nitrogen will just come out from your system. So 3.76 times N2, and since we do not know how much is the amount of air that we are going to burn for the stoichiometric quantity, we keep it as A. And once you burn your biomass, the two major components that will be coming out will be your carbon dioxide, and another one will be your water in terms of like steam, because since it's carried out at a high temperature, the water will be in the form of steam, gaseous phase. Yeah, so it's only this much. So if you see here, we have totally 3 carbons in the reactant side, so that has to be balanced even in the product side. So this will be 3. The coefficient for your carbon dioxide in the product side will be 3, and total amount of hydrogen atoms present in your reactant side is 8. So in the product side it has to be balanced, so the coefficient for your water will be 4. So here you can see the number of atoms of oxygen in the product side. So that will be 3 times 2 will be 6, plus 4 times 1 will be 4. So 6 plus 4 will be 5. Oh, sorry, 6 plus 4 is 10. So here, since you have O2, so the value of A will be 5. I hope you are able to understand. Yeah, so then since the nitrogen is going to come out in your product side as such, so this will be 3.6 times 5. Yeah. So you have got the balance, the equation. So the air to fuel ratio in the stoichiometric quantity will be nothing but 4.76 times your number of moles of air that is involved in the burning process. So that will be here 5 times your molecular weight of air. So since air has both the nitrogen as well as the oxygen component, you are supposed to calculate the molecular weight based on that given percentage of oxygen and the nitrogen. So if you remember, we have calculated here, yes, this one, molecular weight of air. So since your air consists of 79% of nitrogen and 21% of oxygen, here we neglect the contribution from the other different type of gases such as carbon dioxide and other gases which will be present in the atmosphere, since their contribution is very negligible in comparison to these two. So this will be 79%, so 0.79 into 28 plus 0.21 times the oxygen molecular weight. Oxygen molecular weight is 32 and your nitrogen molecular weight is 28. So if you multiply it with their respective fraction and then calculate, the molecular weight of air will be 28.84 gram per mole. So we take this, divided by your molecular weight of the fuel that you are burning. So our fuel here that we are burning is nothing but it's the propane, and the molecular weight of propane is C3. So 3 times carbon's atomic weight is 12 plus hydrogen atomic weight is 1. So 36 plus 8 is nothing but 44 gram per mole. So this is the molecular weight of the propane. So can you let me know what is this product coming out to be, the air to fuel stoichiometric ratio? It's 4.65, 4.76 times 5. Yeah.
It's 15.6.
Yeah, it's 15.6. So now you have your air to fuel stoichiometric ratio, and the air to fuel mixture of the operating system is given as 18:1. Air to fuel 18:1 or 18 by 1, that is 18. Now they are asking you to calculate the equivalence ratio. Equivalence ratio is nothing but your air to fuel mixture in stoichiometric quantities, the whole divided by air to fuel ratio of the mixture, that is nothing but the mixture in your operating system. So here it will be 15.6, that is your air to fuel ratio in the stoichiometric quantity divided by of that mixture that is given in the question, so that will be 18. So 15.6 divided by 18,
0.87.
yeah, 0.866 or 0.87, that's same. So your equivalence ratio for this particular burning of propane with an air to fuel mixture is of ratio 18:1 is nothing but 0.87. So I hope you would have got now like more clarity with how to develop the combustion equation, which is the first and most primary important task for you. Once you know how to develop the combustion equation, then calculation is just nothing but plugging of numbers in the formula. So with this we actually conclude our biomass discussions, and then we move towards start discussing on the concepts of wind energy. So yeah, so wind energy. So if you see, in even in the very first week live interaction session, we had discussed about the solar energy. How does the solar energy, how solar energy can be harnessed, that is in terms of the direct, that is nothing but heating your surface as well as the solar collectors, and indirect way of harnessing is nothing but it's your solar photovoltaic cells, which is nothing but the solar panels that you see in your homes or in major commercial buildings, wherever. If you, when you see a tilted surface, that will be on the rooftop of any building, that will be a solar panel. And since this course is specifically dealing with the solar energy and solar collectors, we do not go for our discussion with the photovoltaic cells. We restrict our discussion only to the direct heating of the surface. But this solar energy also indirectly is utilized by this biomass energy as well as wind energy. So if you remember, in biomass energy, the solar energy is used for converting the carbon dioxide as well as the water molecules to glucose, and that glucose is nothing but is your available biomass. Once you burn that available biomass, the energy that you are going to get is nothing but it's called as a biomass energy. Similarly, for wind energy also, the solar radiation has its own effect. So what happens is, due to the absorption of the solar energy by the earth's surface and the differential heating of the solar radiation during the daytime as well as that of the night time, there will be a differential heating, and due to this differential heating during the day and the night time by the land and the sea, so there will be a alternating heating as well as the cooling cycles that will be happening in the system. So due to this alternating cooling and heating cycles, what happens is a pressure difference is usually created, and this pressure difference usually results in the movement of the air molecules from the land to the sea and sea to the land during the land breeze, sea breeze, during the day as well as that of the night time. So this absorption of the solar energy by the earth's surface and then the rotation of the earth's surface and revolution around its sun affects the or results or creates a alternating heating as well as that of the cooling cycles in the system, and this actually creates a pressure difference between a pressure difference in the atmosphere, which results in the movement of the air molecules from the sea to land or land to sea, and this is nothing but is called as the and then the wind gets generated. So this wind that actually gets generated can be harnessed, and for that harnessing purpose we use something called as a windmill. So here you can see this is a horizontal type windmill. So it basically consists of blades, also called as a rotor blade, and then you have a gearbox and generator and then a tower, and then from this generator you can actually store this wind energy. So the major or the primary principle behind this wind energy generation or wind energy harnessing is nothing but the kinetic energy is actually getting converted to electrical energy. So what does this actually means? So the kinetic energy is nothing but the energy that is actually given by your wind. So once the wind, so the wind has a specific speed, right? So once the wind with a specific speed hits the blade starts rotating, and this rotation of the blade is actually harnessed as the electrical energy. So this rotation of the blade or the energy that is carried by the wind due to the or the energy that is carried by the wind is actually resulting in the formation of the electrical energy. So as I said, there are two factors that usually affect your wind energy. One is nothing but it's the absorption of the solar energy by the earth's surface, and another one is nothing but the rotation of the earth's surface and the revolution of the earth around the sun. So this is the major principle. The kinetic energy is getting converted to your electrical energy, and this kinetic energy comes from the the motion of the air molecules, or nothing but it's the wind. So from there you get so that kinetic energy is what is called is what is going to rotate your blade, and that will be stored as a electrical energy. So this is usually done by this windmill. So we have different types of windmills that is available. So if you see in the course, we have a very detailed discussion on the different type of horizontal as well as the vertical axis windmills. So you have different types of windmills, and their classification is actually based on the way the windmills face the direction of the wind. So they are usually classified into two different types. One is nothing but is your horizontal axis windmill, and another one is your vertical axis windmill. So this classification is nothing but it's going to be on the basis of the direction of your blade and the direction of the wind. So the classification is based on the way the windmills face the direction of the wind. So two classification, horizontal and vertical axis. In the horizontal axis you have many different types. One is your single, double, triple bladed, farm windmill, multi-bladed systems, upwind, downwind. And in case of your vertical axis you have something called as Savonius, Gyromill, Darius, Magnus and Vortex. And the major, so in case of your horizontal axis mill, the windmill blades actually will be facing in a direction parallel to the wind direction. So the windmill blades, if you see these blades, this direction will be facing parallel to the wind direction. Whereas in case of your vertical axis windmill, if you see, over there the way your blades are going to face the air is independent. Like the vertical axis windmills do not the blades actually do not depend upon the direction of the wind. It is independent of the wind direction. So that is what is the basis of the classification. So if you see horizontal blades, horizontal axis windmills, they are usually multi-bladed. Say suppose if you see this windmill, multi-bladed windmill, and they usually have a propeller. So yeah, and they are of propeller type also. So here in case of the horizontal axis windmill, the rotor axis is continuously adjusted to the horizontal direction. So that is how it actually gets its name. So if you see the classification is based on the way the windmill actually faces the direction of the wind. But that word horizontal actually comes from the way the rotor axis is aligned to the direction of the wind. Suppose if they are in the horizontal direction, then it is called as a horizontal axis mill. If they are if they are in the vertical direction as well as perpendicular to the earth surface, then it is called as the vertical axis mill. So let me just write that here. So horizontal, let me just zoom in. Horizontal is nothing but here the rotor axis is in the horizontal direction, facing parallel to the direction of the wind. Whereas in case of the vertical axis windmill, over there your rotor axis is vertical and perpendicular to the earth surface. Yeah. So this is the basis of their classification. Now, if you see, so this classification is detailed very is discussed in much depth by Professor Anandalakshmi ma'am. So if in case if you are more interested in knowing about this different type of axis or the different types of windmills, then you are always welcome to actually go through her lectures as well as the two reference textbooks that are available for this course. Over there, if you see, you have a detailed account on the different type of horizontal as well as the vertical axis mills. So usually the blades, if you see, so since this horizontal axis is a multi-bladed system, it usually consists of around 15 to 20 blades, and these blades are usually 2 to 5 meter in length. So these blades actually consist of airfoil sections. So that airfoil sections are so using that only we actually discuss majority of the concepts related to the windmill. So that airfoil sections, so these blades that is used in the windmill have airfoil sections. So airfoil sections, if you see, I do not have a diagram here, let me try drawing. We do not have shapes. Okay, just a second, do we have a